Okay, welcome back. We saw already the importance of dependability. And now, of course, we would like to improve the dependability of the machines we are building. Let's see how can we do that. First, something very important. All machines, everything which we are doing, they are complex systems and I have a chain of many components. And in order to improve dependability, the first step is to find the weakest link in this chain of components. And here, in the weakest link, you shall invest the effort. When this is not anymore the weakest link, then look for the next and look for the next. This is the normal procedure. There is a ground way of doing this, for example, in aerospace or avionics for aeroplanes. If you take a look how the development is going, then a lot of effort is being invested to improve the dependability of the control computer, of the software, and so on. But if you take a look to the source of accidents, most of the accidents are caused by failures in sensors, especially in the air sensors for the air data system, for the air data computer. But this is obviously the weakest link, but the most effort is being invested in control computer. So you can see, maybe here we have already a very strong link, and here we are investing more and more, and we forget about this weak link. This is a mistake. Okay, then we saw the first task is to find the weakest element, take a look to a statistic of accidents, and focus on this, and then go to the next and to the next. Okay, and there are different ways to improve the dependability. For example, using redundancy. This is a very common way. We say, okay, we have one chain and this chain can fail. We are sure every chain will fail. Then the most simple solution is to have two chains. If one fails, then we have another one. But this will not always help. Sometimes, most of the time, it's help, of course. But there are some failures. First, let's take a look to this mechanical construction. Let's say this is overloaded. This is too heavy. And then first one chain will fail. We have still one chain. But before this weight, this load was distributed in two chains. If one chain is gone, then the load is now on a single chain. Then the probability of failure of this single chain is much more higher than before. So we are not really improving, we're improving, but it's not a safe system. A safe system, or safer, let's say, will be if a single chain is strong enough to carry the whole load. And the second is redundancy. Okay, therefore, let's say the definition of redundancy is what we are doing here to provide more resources than needed for the minimum acceptable functionality. And this will be two strong chains. But it will not help in case of the failures are not independent. We are going to see some examples of this, and some critical components fails. But we have very often the case where failures are not independent. Here I have very nice examples of aeroplanes. Maybe you know about these very famous, both are very famous accidents from the Qantas, from Airbus A380, where one engine exploded, just exploded. And this explosion made a lot of damage in the electronic and the hydraulic on the wing. So we have a lot of failures. Even if we have redundant systems, redundant hydraulic and so on, all these devices were not accessible anymore because of this common failure. This explosion here made a lot of damages here. Or another very famous case is this Airbus 300, which was just shot with a rocket, with a ground-to-air rocket in Baghdad. They were carrying goods in the time of the war in Baghdad. So it was hit here and it destroyed all three hydraulic systems. So when one hydraulic system fails, okay, you have another two, and then you can continue controlling the aeroplane. So you have redundancy, and you think it shall be okay. But in this case, all three redundant hydraulic circuits was destroyed. So there was no redundancy, no hydraulic control anymore. So even if they have implemented a very good redundancy, it was not possible to control these aeroplanes by the control surfaces anymore. It was a very big art of the pilots to survive this and to land these aeroplanes. It was a very famous case because it was almost impossible. And the reason is it was a common cause. This cause destroyed all redundancy. Or for example, this is another aeroplane shooting in a war region. For example, if you have here a lot of redundancy, of computer redundancy, the computer bay is here. It was not directly in the computer bay, but assume this shot will be here, directly on the computer bay. In the computer bay, you have a lot of redundancy. Every service is provided by maybe 4 or 5 computers, so you can be sure nothing can be wrong. So if one computer fails, we have another 3. In 3 computers fails, we have still 1. But if this rocket will shoot here, the avionic bay, then a common cause, all redundancy is destroyed, so this will not help. Okay. And now let's see the definition of dependability and what are the components and the parameters of dependability. And now, if we are talking about dependability, let's see what is dependability. What are the different parameters on dependabilities and what is what we have to handle. Let's begin with the beginning. Okay, the dependability treats these cases of states. It treats faults, errors, and failures. And maybe it sounds very similar. And because it sounds very similar, I made the translation here, so you can see if it is clear what is the difference between fault, error, and failure. But to make it clear, I'm going to explain this in more detail. Okay, let's talk. We have 2 different definitions. The hardware people and devices and constructions, mechanical constructions, have this kind of definition of the way from fault to error to failure. And on the other side, the software people had another definition. They begin with error, a programming bug, some buzzbill, and then we have the chain until we have the failure. Here in hardware, everything begins with the failure, and after the failure, we have the error. Okay, let's see first the mechanical definition or electronic or hardware devices. Well, we have the fault, something doesn't work anymore. At the beginning it was working, but it breaks or something like this. Then from the fault we have an error situation, a behavior or a situation which shall not be. And this is per the definition of error on this side of the graph. And after the error, after this situation which shall not be, we have a failure. And this is what we see from outside of this module or this system. Something doesn't work anymore, and then we see it has failed. And this can be repeated. It can be a chain in the different levels, in the different components of a system. A system can have different subsystems. Let's assume we are talking about one subsystem first. Let's say, let's take an example of aeroplanes, and very simple, only 2 steps. Let's say we have the air data systems and the aeroplane. Of course, we have much more than that. Below the air data systems, we have many other subsystems. But let's make it simple. So we have air data system and we have aeroplane. Okay, then something can go wrong in the air data systems. Maybe the processing unit will fail. Then we have an error situation. It's not behaving as expected, and then it doesn't work anymore. From outside, we see we get no data anymore from the air data systems, air data computer. And this will be a failure for the next, a fault for the next level. Let's say the aeroplane. So the aeroplane, inside of the aeroplane, there is a fault. If we have no air data then we have a very erroneous error in the system. We don't know how to control it, and then we can have a failure of the aeroplane, and this can go to hazard and to accidents. So this is how we can repeat this, the same, in different levels of the system until at the end we have, I don't hope so, but we could have an accident. On the other side, on the software, everything begins with a programming error. The programming error is there from the beginning. So the machine is working properly, but the error is already there. There is something wrong, waiting for the right moment to be activated and produce an effect. So when this error, which were there from the beginning, is triggered, then it will produce a defect. Something is behavior wrong, and then we can have a failure of the whole systems. So there are another definition. We begin with an error, programming error. Then we have a fault. Here is the opposite. First the fault, then the error. But here, first the error, then the fault. Something doesn't work anymore, like this. And then we have a bug, which is already activated. Then we have the failure. And then we have the defect or the accident. So, it's not really important. You shall only know there are two different definitions of this chain from fault, error, and failure, depending if you are talking to mechanical construction or electronical people, or if you are talking to software engineers. It's different, but it's not really so important. Okay, then let's see the classification of faults to failure. First, we have a fault, a defect within a system. Something has failed. Then an error, a deviation for the required operation in the system or subsystem. So it's behavior. The behavior is not as expected. Then we have the failure. And this is the component doesn't provide the service anymore. And this, the failure, is the first thing we see from outside. From outside, we don't see there is a fault. We don't see there is an error, something is not behavior inside of the system properly. Here, when the system fails, at this point, we see from outside there is something wrong, not before. And then we have an extent, we have local failures and distributed failures, of course. Okay, and these failures can be in value and the duration, the classification. In value can be it was determinate. It's a clear case. This is a wrong response, or it can be indeterminate. It's random, so every time it will behave in a different way, so varying values, a very the worst situation we can have. And the duration, it can be transient, intermittent, or permanent. We are going to see this in the next slides. For example, this is the chain. We go from here to here, and in between, if there is a failure, we are not going to be able to provide our service. Okay, now the next. This is what it treats. The dependability treats these cases, fault, errors, and failures, as defined before. Now the attributes of dependability. This is something we saw in the video before. The attributes are availability, reliability, safety, confidentiality, and integrity. And I hope you remember the definition of these things. If not, go to the previous slide and see the 5 columns of dependability. Okay, and the means, how can we provide dependability? How fault preventions to avoid faults. So if the system has no faults, then it will be dependable. Or we know it will have faults. We cannot avoid this. Then we have to implement fault tolerance. Even if something fails, then we have something which will take the work, the task of the failed components, and we continue working. Then the next thing is fault removal. So after something has failed, using fault tolerance, the system can continue working. But if we leave the failed part there, then we are losing redundancy, and the next failure maybe will not be tolerable anymore, and then we have the accident. So therefore, fault prevention, the first step, then fault tolerance. Even if we have done everything to avoid faults, something was wrong, then we have the tolerance. And then the next, this is a part of the maintenance of the system, correct or remove this fault or substitute the component. And something very important is maybe we don't need to wait until the fault occurs. We have some means for fault forecasting, so we can predict. There is a lot of statistic values when things are going to fail, and we are monitoring the behavior of the machine. And if we find, for example, some vibrations which shall not be there, we can take a look to the statistics and see after these vibrations, these components will fail. Or we know this component is producing this vibration, so we don't need to wait until this failure occurs. So before the failure occurs, we know it will come. Using all the statistic measurements, then we can remove the part which will fail next. Or we know, okay, every component will be able to work, if you will look at the statistic, only so many hours. And then before we reach this limit, when these components fails after so many hours, we substitute this component, so we avoid the fault. Of course, we cannot be sure. Anything can fail at any time point. Okay, and here goes, we see everything is going around faults, because fault is the beginning or the trigger of failures or accidents. So everything will begin with a fault, and we have then a chain of events. First, maybe a very small fault, but it will produce a chain of events until we have the failure, system failure, or maybe an accident. So let's begin with the beginning. How does an accident begins? With a very small fault somewhere. Okay, first let's see the cause or the different parameters of faults. First, phase of creation, or when the fault begins. It can be from the beginning there, if it is a development fault. So from the beginning it was there, but it was not visible. Until some circumstances arrive, then this fault will be visible, and then we have the failure and maybe the accident. Or it can be an operational fault. So at the beginning the design was right, but the way how the system is being used is wrong, or the environment has an unexpected situation. Then we have the system boundaries, where the fault comes from. It can be an internal fault, or it can be an external fault. So it can something from outside come into the system to make the perturbances, or it can come from inside. A screw breaks after so many hours of use, and then we have the internal fault. Then we have the domain, where the faults begin. Maybe mechanical, or electronic, or software components. And so it's the beginning. The beginning could be software, and then we can have a mechanical failure, and then we can have a system failure. Or another important thing, the phenomenological source of the or cause of the fault. It can be a natural fault, for example, lighting, or it can be a human-made fault. Someone with bad intentions, sabotage, or someone who is using the system in an inappropriate way. Then we are talking about people now. Then there is an intent. If it was human-made, then we have two options. It was an accident. He was not he didn't want to make something bad, but he was not able to do it better, or he was not well trained and he didn't know how to operate the machine. Or it can be sabotage, people with bad intentions, deliberate, malicious faults. Okay. And the persistence of the fault, we are talking about this. It can be permanent, it fails and then it will stay for always, or it's transient, it comes and goes, it comes and goes. We are going to see this next. Okay, then let's see the persistence of the failures. I said before we have two different types, permanent or transient. The transient has other classification. And obviously the most typical cases for permanent are mechanical failures. If something breaks, it's broken for always until you repair. Or electronic failure. So electronic components fails and they don't work anymore until you repair. We have in software sometimes, and in hardware some time of transient failures. For example, a broken cable. And sometimes you have contact and the things are working properly, and sometimes the contact is not there, then things are not working, and then you have contact again, and so on. And it depends of the movements of the system. So sometimes you will have contact and then there is a vibrations, no contact anymore, vibrations again contact, and so on. It's very difficult to find. So these are transient faults. They are coming and they are going. Here I have a graphic. Let's say this is the timeline. Green is everything is working properly, and red is it is not working, a failure, a fault. So a transient, everything is working. Suddenly it doesn't work, and it works again, and it continues working. Maybe it will not repeat, or maybe again sometimes. Okay, then we have the intermittent fault. The intermittent fault, it's not working. It's working, then it stops working or works in a wrong way, and then it works again properly, and then it breaks again, and again not repairs, and they're working properly, and so on. And this is random. So after one failure, you cannot say when will come the next failure, on how long it will be out of service. So this is an intermittent fault. On the permanent fault, the most simple, it was working properly, then there is an event here, and then it stops working for always until you repair, like here and like here. And these other are, in this case, transient errors. Okay, now the sources of faults. It can be a designed error, so from the beginning, the failure was there. The fault was there, only waiting until it's seen. For example, this is a case of ground design. The one who made this plan make it wrong. Or manufacturing problems. At the beginning, the design was right, but implementation was wrong. This is a real case. For example, a measurement error, or there is a deviation in the process, or who knows what, and at the end you have a system which is not working properly. It can be, the fault can be from external disturbances. Inside was everything working properly, from outside you get a hit, a rocket, or something like this. Or maybe without intentions, only harsh environment conditions, corrosion, or wind, or radiation, or water, or too cold, or too hot, who knows what, but the environment was harsher than expected. Or the system is not used properly, misuse of the system, going beyond the parameter, beyond the operational parameters, or maybe with bad intentions. Okay, the sources of faults, it can be a mechanical, for example, wear out. It's moving and moving, working, and someday it will break after so many hours of use. It can be a deterioration, for example, wear out, fatigue, or corrosion, or a shock, something like this. It breaks suddenly. Fractures and overload, for example. This is mechanical failures. Then we can have electronic failures, bad fabrication or wear out. So these are, for example, latent defects. From the beginning it was there, but it will be active under some conditions. Or operational events, noise, heat, electro interferences, and so on. Or a design defect from the electronic. In software, we have from the beginning the error there. It's a bad design from the beginning. So it can be a design error. Maybe you made the design right, but when programming you make a mistake. Instead of 1.3, you write 1.4, and then you have a mistake. The design was properly, but the coding was wrong. Or coding rot. And this is another situation, accumulated runtime faults. If you are storing data and using the stored data to take the next decisions, if there are some deviations, all this will be stored, and after a long time of operations, then the deviation from the right data to what you have is so big, then you might have a fault or even a failure. Or it can be mechanical, electronic, software, or people. The operator with good or with bad intention. Okay. And now let's take a look to the failures. Up to now, we were talking about the beginning of the catastrophic, of the accident. The trigger was the fault. Do you remember? We have this situation. Everything begins with a fault. Then we have an error situation. And then we have the failure. Okay, we were talking about this. Now let's talk about the failures. Okay, then we have the propagation, something went wrong, and the failure or the fault will be propagated in the system. And at the end, we have the failure, and this is the symptom or what we see from outside. Okay, then we have a domain. Where can it be? It can be a value domain. The system produces a wrong data, or it can be in the timing failure. It produces the right data, but too late or too early or too different or unexpected. Then you have the controllability of the failure. Maybe it can be a controlled failure. That is very good. So the system recognizes something is going wrong, and it takes an emergency action to avoid an accident. Or it can be just uncontrolled. If something fails, who knows what will occur? The car will go outside of the street and then you have the accident. Here, controlled, maybe the car will reduce its speed until it stops in a controlled way. Okay, and the consistency of the failure, it can be consistent. It will be with the same input situation, the same reaction. Or it can be inconsistent failure. So very difficult to reproduce the same environment, the same inputs, and different reactions. And after all this, we have consequences. Maybe nothing, minor failure, or it can be worse and worse until you have catastrophic failures with accidents, people injured, or maybe people dead. So this is from nothing to very catastrophic situations. Okay, on all of this, what we see from outside, that is the effect, or we can say the visibility or the symptom of the failure. It doesn't matter where does it comes from. What we see is, for example, a false alarm, okay? A degraded service, not so bad, is reducing its service to avoid an accident. A safe shutdown, something similar, it is reducing until stop. For example, an atom reactor, if something goes wrong, it reduces and stops, shutdowns the nuclear reaction to avoid an accident. So you will not get energy anymore from this atom reactor, but you have not an accident, which is a very important situation. And then we have signalate failure. So before it fails, you send a warning. Warning, it's going to fail. You give the signal before, so the operator can be ready. So the system had their own diagnosis to see something is going wrong. I can keep it working for a little while, but not so long. So you report, be aware, it will fail. The opposite will be the unsignaled failure. So without any warning, failure stops working. And this is something like a crash failure. So suddenly you have a crash, suddenly it doesn't work anymore, and there was no warning. And then we have a very, let's say, bad situation of failures from sensors, for example, and these are the deceptive failures. And this is the system, the failure, the sensor, or whenever you want, is producing data. It seems to be right, but it's wrong. So it's sending wrong data, but you cannot see it's wrong. You can trust, you are trusting this data or this behavior, but it is wrong. And if we take a look to the number of accidents in aeroplanes, a lot of accidents comes from these deceptive sensors. Sensors which are producing data, it seems to be right, but it's the wrong data. A very common case is the angle of attack. So you can see how the aeroplane is flying. If we have several times the case, it is frozen, it doesn't move anymore. So even if the aeroplane is changing its angle of attack, this device will continue reporting you are flying, for example, horizontally, even if the aeroplane has an angle of attack like this, or a pitch angle like this. And then you think, okay, everything okay, but if you are increasing the angle of attack too much, then you can have a stall, and then the aeroplane will fall down, and you have an accident. So this is the reason of, I know at least two or three such cases where the angle of attack sensor frozen. It was reporting data and saying everything is normal, but this data was wrong. So deceptive failure. Okay. Now let's talk about the root or main source of failures. You shall know the first enemy of dependability is complexity and complicated systems. Let's make a difference between complexity and complex and complicated. Complex is, let's say in few words, my known definition. Complex is it has many components, many parts. And complexity is it's difficult to understand. And both are dangerous. Complex is dangerous because if any of these parts fail, then we have a failure. The system will fail. And complicated is dangerous because if no one understands what it does, how it works, then do not surprise if it will not work properly. It's normal. It will not work properly because no one knows how it works. So both are dangerous. First, let's talk about complexity. Complex. Why is complexity a problem for dependability and reliability? Okay, and I think we are already searching the limit of complexity. Let's talk about transistors and embedded microcontrollers, for example. But you can apply exactly the same for any other things which has many, many components. For these computations, they work only if all components are the same or all components have the same failure rate. About failure rate, do you remember we were talking a few videos before? I'm going to go back just a second. Where is the failure rate? Here. This was how many failures per hour can we expect? And this is the failure rate. And this is something 10 to the power of minus n. Okay. And we are talking about a time unit. And this time unit can be seconds, days, hours, whenever you want. But be aware to do not mix these time units. When you are talking about hour, for all computations, you shall continue talking about hours and do not switch to seconds. Okay, let me see. Oh yeah, here was the planes. Okay, I said before, these computations assumes all components which we are considering have the same error or failure rate. If you have mechanical and electronical and other components, it will be difficult. And it doesn't apply for software. For software, there is no metric up to now to say what is the reliability of software because it depends how well it is tested and how often or if you trigger exactly the failure, or you can use the software many years without triggering the error. So up to now, there is no reliable way to quantify the reliability of software. Okay, but now let's talk about hardware, in this case transistors, and millions of transistors. Let's say the reliability of a system with n transistors, n is in this case millions of billions, and each of them has a failure rate of lambda. Okay, the probability it will work for 10 seconds or hours. Do not forget to use exactly the same time unit like here. Let's assume the failure rate was in seconds. Then the probability it will work for 10 seconds is E to the power of minus n, number of transistors, multiplied by the error rate, multiplied by the time which you want to use the system. For example, you started and you would like to be flying for 10 hours, then here you can compute what is the probability it will work for 10 hours without failure. Okay, and if you make a plot of this form, then you will get something like this. This is the number of n, number of transistors, multiplied by the time which you want to use. And then you can see it's almost okay, but then at one point it breaks abruptly and it goes down. So when we are approaching to this point, this is 10 to the power of 8, then after this, the reliability of the system will decrease rapidly. So as long as we are here, then it's okay, but be aware, if you are adding more and more components, we are approaching to this point where it is going to go down. If we want to have high reliable systems, then we have three chances. If we take a look to this, reduce the probability of failure of each component, which is difficult because I assume we are doing the best to get for each component the highest, the lowest failure rate, or reduce the number of components, which maybe is possible, or reduce the time of operations. But the time of operation is given. You want to fly 10 hours, for example, and don't you like to know the probability of that the system will be working for these 10 hours? So the only thing you can do is reduce the number of components, and then you can increase your reliability going in this direction, or add redundancy. This formula is only for one chain. You have 2 or 3 parallel chains, then the probability that all of them are going to fail at the same time is very, very low. Okay. Then let's say you have done everything what you can and the system fails, which I will say is something normal. Then a system fails is something normal. You should not be surprised. Okay. And then everybody will ask, why did it fail? And who made something wrong? Maybe the analyst, the designer, the programmer, the tester, or the operator. Who is guilty? Who made something wrong? Or maybe it was a normal accident. And that's a problem, because the question is, who made something wrong? So everyone is trying to find who is the guilty, and he will be claimed. But that's not what we shall do. What we shall look for is how can do it better, something like this. So do not try to find who made something wrong, but to find the source of the accident, of the failure, to make it better. Okay, let's take an example. This, by the way, this is a bomb. And okay, and we are transporting this bomb with this forklift, and we have an accident. Then we can ask, why did we have this accident? Maybe there was a requirements gap. The one who designed everything, including the transportation of the bomb and this building, make a mistake. Or maybe the requirement was right and there was a design flaw. The one who made the design of this building make a mistake. Or maybe an implementation's error. Someone forgot to do something. Other procedural error. You define how to transport the bomb from inside, maybe to the truck, a mistake, or an operator error. The procedure was well defined, but the operator just ignored and they made something different, or unexpected environment. Now we can talk about what went wrong. What are the possibilities? Maybe there was a requirement gap. No one required to have here a protection. For example, maybe we shall here a fence to avoid this truck to go further. Or maybe, okay, this will be a requirement gap. Or design fall. Maybe the requirements say we shall have here something to protect the truck to fall down, and the one who made the design didn't talk about this and made the design of the building without considering this requirement. Or maybe in the design it was a fence here, but the one who built the building forgot to make this fence. Or maybe it was okay. There shall be no fence because maybe another truck shall here come, and you shall transport the bomb only if there is a truck here. Then a procedural failure. When you define the procedure how to bring the bomb, you shall say take it only if there is a truck here, a truck. Or do not, or be very carefully when going out of this door, turn to the right immediately, for example. Or maybe it was defined and the operator just ignored this. The operator just took the bomb without looking if there is a truck here waiting, or forgot just to turn right. Or an unexpected environment. Maybe normally is something always here, and it was removed. And no one report, maybe there was a ramp here and the ramp was removed, and there was no report, the ramp is gone. And he, like every day, was taking this ramp down, but today the ramp was not there. Then it was unexpected environment. So you can think what was the mistake. And then maybe you can, the first idea shall be the operator. He made the mistake. He was crazy doing something like this, but maybe the error was something different. It was always a ramp here, and no one report the ramp is gone. Or the designer shall design here a fence, and he didn't it. So remember, until you have the accident, there is a long chain of events. It's something like this. You have an accident, but only one event is not enough. If you make an analysis of accidents, you will see it was bad luck. This, and then this, and then this, and then this. And for big accidents, you have a chain of maybe 100 different events until you have this bad situation or accident. Only one or only two is not enough, or only one missing of all these events will be enough to avoid the accident. Okay, let's say, yeah, and it doesn't mean that any failure will cause the accident. It's only the trigger. Let's take an example how it works. Let's say this is, I made this in a one-dimensional chart. This one dimension is the time, and the other dimension is the state of the system. This is what we expected, that is the green corridor. So here the system, the state of the system shall stay here. Then we have the yellow corridor. Something is wrong, but it's not critical, but we shall be aware. And in the red area, then we have a failure. Something went very wrong. And here I have only one dimension. This line is moving in time and one value here. But a real system is not a one-dimensional system, it's a 100-dimensional system. So we have 100 variables, or yes, 100 variables or 1,000 variables, I don't know how many of them. And for each of them, we have a corridor where it shall be, and if it goes out of this corridor, one of these 100 variables in an 100-dimensional space, then we are risking maybe a failure or even an accident. But for simplicity, let's take only one variable, only one dimension. So the system is performing like this. It's inside of this corridor, and maybe here occurs something wrong. But it doesn't mean that this fault will immediately cause the system to go to the red area. It will take time until it crosses this green corridor, and then we can detect something is going wrong. But the effect, the fault was some time before. But maybe it is not so bad. Maybe it will continue working like this and will come back to the green corridor, and then everything will be normal in normal operations. But okay, and now let's talk about this time from here to here. Let's take, for example, a software error, a bug. It was from the beginning there. So it was already programmed, this failure. So the failure was already programmed. So it was just waiting for the right moment to explode. For example, if you have something like this, an open cord at your shoe, you can go 1,000 steps and nothing occurs. But the failure is already there, just waiting for the moment, and then you can step on this and then you have an accident. It's something like this, or immediately. Or you can go 1,000 steps, the stone is already there. When are you going to stumble on these stones? It can take a long time, and then you stumble. So this root of the fault or the failure can be much more, many years before the accident occurs. Let's take an example. Do you know the accident of Apollo 13, the chain of events? It was a very interesting mission from the Apollo missions. They had an explosion. They were flying to the moon, as you know, but this mission didn't land on the moon. They have this accident, this explosion, and they went around the moon and came back to the Earth. And it was really, really difficult to bring these astronauts on life back to the earth. Do you know about this case? It was a very interesting, well, many years ago, but let's take an analysis of the event of the chain of events until we have this accident. The mission Apollo Tryson flew, I think, 19,070. But the chain of errors began 5 years before. So 5 years before the accident, it was the first mistake. Okay, and it began in 1965, 5 years before the mission, and the power supply was changed from 28 volt to 65 volt 5 years before, and a very big mistake, they didn't say it. So they just changed the power supply without making any report. Okay, then the problem was the manufacturer of the oxygen tank was not informed. So the manufacturer of the oxygen tank made a heating in this tank thinking he will get 28 volt, but he got 65 volt. He didn't know about the change, this modification 5 years before. Okay, and the tank contains propeller for mixing the cooler, a semi-liquid oxygen, which is very cold, and a heating element, a thermostat, which switches over 25 degrees. Okay, and the oxygen tank number 2 was already used in Apollo 10. It was mechanically damaged. Apollo 10 was a pre-mission to the moon, but they reused these components. So it was already damaged when landing 3 years before. The landing of Apollo 10 was in 1968. And this damage was not investigated. So they took the tank. Okay, it's okay, let's use a... Okay, and then we have the day of the launch, the day of the start. All this was years before. And in this day of start, okay, the cryogenic oxygen, this is very cold oxygen in liquid form, remained in the tank. They forgot to empty this before the start. And the tank was heated. So it was a heater to keep a temperature of 25 degrees, but it shall be not an exceptional case. But in this case, they forgot to empty the very cold oxygen, so it began heating. And it was heating for 8 hours. And the system was designed only for 28 volt, do you remember? But it has 65 volt. And the cable was fused. The cable broke because of this high current. The result, the current was not able to be measured anymore, and the temperature of the tank reached 370 degrees. And the normal operational temperature was 27 degrees. And it was 370 degrees after 8 hours of launch. So they were already on its way to the moon. And then there was a detector which the temperature is very high. So it started after 55 hours of operation, a fan, als cooler. But the fan was not designed for 65 volt, the same problem like the heater. It was designed for 28 volt. So there was a shortcut. And the shortcut make a spark inside of the tank, which has a very explosive mixture of alcohol, of oxygen. And this oxygen, it negates and the tank explodes. And when this tank explodes, there was a redundancy. This was one tank, this was tank number 2, and there was another tank, there was tank number 1, but they were together. So the explosion of this tank damaged the other tank. So they lost all oxygen on board. So it was a very terrible situation. They was almost lost. So no oxygen anymore, or very limited oxygen, flying to the moon, already 55 hours on the way to the moon, and almost no chance to survive. But it was a very impressive action how they rescued these astronauts. But in any case, take a look. The root fault began 5 years before, and it was a chain of events until you have the accident.